So, what is so noisy? Oh, it's the projector. It's really thinking hard about something. So I'll begin. Dear Father, we thank you for this day, and I thank you for this class and your creation, that we are able to understand it and study it. Just pray that you be glorified in what we do this day, Lord. In your name I pray, Lord Jesus. Amen. So I was thinking, well, one of you guys came to ask me questions during office hours, which was like, whoa, I have students. They have questions. It happened. A student actually came to office hours. Like, whoa. It's actually kind of rare these days. Go figure. But I guess I don't assign enough homework. That's the problem. But I do in my other classes, and they don't come there, you know. Okay, so one of the examples I have failed to run into yet is the charged plane. Right? Suppose you've got, here's a conducting slab. All right? Conducting slab. All right? And suppose that you have surface charge density, sigma, right, on that conducting plane. Now, I don't really need to tell you that it's uniform. It has to be uniform because charges are free to move around on the conductor, right? So if it wasn't uniform, they would rearrange themselves until they were uniform, all right? So this is the assumption that we have a certain amount of charge per unit area there. Then the question is, what's the electric field, right? What's the electric field? So what we do is the usual thing. We think about maybe drawing like a Gaussian. This case we'll do like a pillbox, like this. So here's where it intersects the plane, right? And then down here below the surface, inside the slab. So this is like inside slab, okay? But we talked about this the other day. Inside a conductor, what's the electric field? Electric field 0 down here inside the conducting slab, right? On the other hand, by symmetry, the electric field has to be going directly up perpendicular to the slab, right? It can't have no perpendicular. Excuse me. There can't be any like parallel component to the electric field. It has to be directly up. If it was any way parallel, then the charge would be moving. The electric field would be pushing the charge around, but it's not. It's a static situation. So the electric field looks like this. All right? And so the only place in this Gaussian cylinder where you're getting flux non-trivially is up here. Right? Now, if this is the area A, then the charge enclosed right here is what? Charge enclosed is, what is sigma? The meaning of sigma is what? Yeah, it's dq dA, right? So, and that's uniform. So this Q enclosed, we can just do sigma times A. That gives me the charge enclosed. And then Gauss's law. So Gauss's law tells me that the flux through the Gaussian pillbox is equal to the charge enclosed divided by epsilon naught. But that here means that E times A is equal to, well, sigma times A divided by epsilon naught. What's that give me? The electric field is equal to sigma over epsilon naught. And of course that's directly perpendicular to the plane. Yep.
And if we were to not have this be a plane on a conducting slab, but just a plane with charge, wouldn't it be like E sigma over, or sorry, E is equal to sigma over 2 epsilon naught, because charge is going on both sides?
That's right. So if we had, instead of a conducting plane, we had an insulating sheet, right? Like this. Then the deal with that, if we have sigma, charge sigma uniform over the insulating sheet, so it's just distributed like that, then you're right, you've got electric field lines going like that, you've got electric fields going down that way, right? And so we worked it out. In that case, we get the calculation that Q enclosed divided by epsilon naught is equal to, again, sigma A over epsilon naught. But the difference here is that the formula for the flux is 2EA, right? So therefore the electric field is sigma over 2 epsilon naught for charged sheet. And so, excellent follow-up question. These are two very different situations, right? Because with a charged insulator, the electric field goes above and below. So the field lines from the charge get to go either up or down. But with the conducting one, all of the field lines only go up away. None of them go into the conductor because the electric field is 0 there. And that's the difference. So these are formulas that you should be able to, on the one hand, derive, like I just did, okay? And also, you should just be able to like know them and apply them to other examples is also the situation. Oh, let us attend. Here you go. Oh, I guess I should top hat, huh? One moment. I will get it. So you guys have any questions while I'm finding this exciting code for you? I have an example, like I think it was problem 8 in the mission. I was going to show you what's involved there. There actually is some calculus, and I didn't quite do it. I was going to spend class time on that earlier, and I just got distracted with something else and didn't do it. I mean, I've started to talk about what you needed, but I didn't really quite finish it. So I'd actually like to work a similar but different problem so you can see how to work the problem in the mission, okay? So we'll do that in a second here. 5132, them's the digits. 5132. I'm not quite, like I've been sitting in Dr. Schmidt's class, and he likes to take these and look up something on Google to ask the students some kind of convoluted way to get them to put the code in. I don't have, my top hat game is not there yet. I used to scramble them when I had a small class. That was fun. I would tell all of the students how they were scrambled except for one student, because it was a class with 3 girls and 1 boy, and so the girls were on this like group chat, and I just tell them the cipher for the top hat code, and the boy we would just not let know, and we just sometimes wouldn't let him even attend. But it was okay. It was good natured. Let's see here. All right, I will find. Just a second. I scanned so your peer who came to talk to me today. This will be kind of boring for you because we already looked at this today. I'm sorry, but and I will post this in. What's it called? Canvas. Once I get a chance. Hopefully there's no mistake in here. We'll find out. I did get the same answer 2 different ways though, so that's probably a good sign. Come on. There we go. So let me turn off the lights in here for just a second so you can relax. So, all right. How do you actually calculate the flux through some surface directly by calculus? All right. So the way that's done is what you have to have to calculate the flux through a particular surface like S. You need to have what's called a parameterization, right, of the surface. And so what that means is you need a formula like R of UV that for the input UV, it puts you at a point on the surface. All right. So think of the R vector as like a way of taking a rubber sheet, which you could think of the domain of the parameterization, and then like stretching it out in 3 dimensions to make the surface. That's what the parameterization should be thought of as. And so the formula for the parameterization of a sphere is given right here. Now, truth in advertising, I'm using physics conventions for angle, which is that theta ranges from 0 to pi and phi ranges from 0 to 2 pi. That's exactly backwards of your Calculus 3 class if you're in there right now. My apologies. But this is actually the common convention in engineering and physics. You should be aware that there's two conventions, because if you don't know about this, this will get you at some point, right? So look, if you take these three formulas, this for x, this for y, and this for z, if you look at x squared plus y squared plus z squared, what happens is the cosine and the sine squared collapse together, and the first two terms, sums of the squares, gives you an r squared sine squared theta. And then you add that to r squared cosine squared theta, and sine squared theta plus cosine squared theta is 1. So if you look at it, when you add the squares of this, this, and that, you get r squared, which means that it is in fact parametrizing a sphere. Another way to understand this is that these are just the spherical coordinate formulas, and you're setting the spherical radius equal to r. That's how you parameterize a sphere. Anyway, if you look at page 28 of the lecture notes, I have the complete calculation there. And there, what I calculate is that the cross product of the partial velocity with respect to theta and the partial velocity with respect to phi, these give you two tangent vectors to the sphere. The cross product is then perpendicular to the sphere, which means it's in the normal direction. And as such, this gives us r squared sine theta r hat. Now you might wonder what r hat is. R hat is a radially outward pointing unit vector. We have talked about this in here. I sporadically put it on formulas, don't I? So there it is. The infinitesimal area element for the sphere is simply r squared sine phi d theta d phi r hat. And so if you wanted to convert this formula to like calculus 3 angles, like math angles, it looks like this: r squared sine phi d phi d theta r hat. Maybe I should put a rho hat to be more regular mathy. Anyway, what that means in more detail is given right there at the bottom, okay? So this is the infinitesimal area element for the sphere. You got your r squared, I'm back to my physics coordinates, r squared sine theta, and then this is a unit vector that points radially outward, okay? That's the r hat. These formulas are basically linked to putting x equal to this, y equals to that, and z equals to that. So now let's get to the calculation. So I'm trying to calculate the flux of an electric field. I made one up that's like your mission problem, but different, okay? So the one in your problem is a little bit different. The one in the mission is actually even easier than this. So here we go. I made the electric field 2x, z, and y, right? That's, you know, and I'm not putting in, I should, if you wanted to fuss, I should put in dimensional multipliers, like this is unphysical, it's not dimensionally consistent. Guilty as charged. Take points off me. I'll take plenty from you, I'll give you some back. Maybe I'll curve the next test like 3 points with respect to my lack of units on this example. Does that seem fair? So you're like, you should like leave units off more, right? Okay, good. See how this game is played. Very good. So what I do is I put the x formula here because the vector field's given to be 2x. So this x goes here. That's the x formula. This is a z, believe it or not. So z is r cosine theta. So I put a, now I don't put little r, I put big R because we're on the sphere where little r is equal to big R. Okay? So I put that there. My last was y. The formula for y is here. So I put, you know, big R, little r equal to big R because we're on the sphere. Sine phi sine theta. Now over here, I couldn't fit it onto the paper, but I've got the spherical area element, r squared sine theta times this contraption. All right, that's all here. Now I need to take the dot product of the dA with the E evaluated on the parameterization. All right, and when I do that, you know how to do dot products, right? This times this gives me that. This times that gives me that. This times that gives me that. Take a dot product. And again, I'm going to post this PDF in Canvas for you guys, so you can look at it there if it's helpful. I just want to talk through it with you here, because we're here, right? Sorry, I have not had a chance to white out stuff, and I probably am not going to. If you can suffer through my scribbling, I think it'll be okay. So I did some algebra, and I get 2r cubed. This gives me a sine cubed theta cosine squared phi. And then it turns out, after you take the dot product, these are actually the same thing 2 times. So I just do a 2 r cubed sine squared phi sine phi cosine theta. All right. Now this is an integration over the two spherical angles, right? And for those of you who are in Calc 3, who've already taken Calc 3, okay, I'll allow it. For you who've already taken Calc 3, you might remember, well, when the angles have no dependence on coordinates, it's super easy. You can just basically, if your integrand also is separable, you can just multiply the integrals of each individual, coordinate function. There's like the iteration of the integrals is much simpler in this particular case, and this is that case. So this double integral is equal to the product of the integral from 0 to pi of the sine cubed theta d theta and the integral from 0 to 2 pi of cosine squared phi d phi. On the other hand, over here we got integral from 0 to 2 pi of sine phi d phi times the integral from 0 to pi of the sine squared theta cosine phi d phi. All right, but this is wonderful because that is 0. If we integrate sine over a full cycle, 0, which means only the first term matters. And if you tilt your head and squint, you can see that that's 4/3, and that's pi. That's a joke. Like, those are a calculation. I can explain the one, but I'm omitting the calculus there, but the calculus is calculus 2 that you guys all know. Right? To integrate sine cubed, you do sine squared times sine. You convert the sine squared to 1 minus cosine squared. You make a u equals cosine substitution. It's just that integral. The integral of cosine squared, of course, is 1/2 1 plus the cosine of 2 phi. And when you work that out, it gets you pi. These are integrals you can do. So I get 4/3 from that. I get a pi from this. I get the 2r cubed that was there all along. And I get 8 pi r cubed over 3. That's the flux of this electric field through the sphere. Now, there is another way to do this, which is easier, which is to use the divergence theorem. You're like, well, I haven't finished Calc 3. I'm not allowed to use the divergence theorem. I don't have the life experience, right? Like, it would be insincere for you to use the divergence theorem at this point in your life because you haven't finished Calc 3 yet, right? Hopefully someone on your team has finished Calc 3. And you can leave it to that person to apply the divergence theorem because it's like way, way easier. Check it out, yo. The divergence of E is the x derivative of the x component plus the y derivative of the y component plus the z derivative of the z component. But these two are 0, which just leaves us with a 2. You pull the 2 out, you've got the integral of the volume. What's the volume of a sphere? 4/3 pi r cubed, right? So we get 2 times the volume. This is the ball of radius r. 2 times the sphere's volume, really the ball's volume. And what do we get? Well, we get, yet again, 8/3 pi r cubed. All right? So what I'm telling you is to do that problem in the mission, you could either do the second way or the first way. Like, it's up. I mean, I'll be fine with either way if you want. I think now that I've said that, I will get 0 solutions the first way, I'm pretty sure. Let me check on it. Where was I? Physics. Mission 2, right? All right. So yeah, like this is the problem I'm talking about. I'm trying to help you guys out with this problem. So you notice this problem has the electric field is y, 3x, z. It's almost the same kind of example that I just showed you, right? So you can either use the parameterization and work out the double integral, which could be very satisfying. You'd feel like you really did something, right? Or you can apply the divergence theorem. And if you do that, what's the divergence of this electric field? 0 plus 0 plus 1. The divergence is 1. So what's the flux? It's what? 4/3 pi r cubed. Yep. So this is a very easy problem after we've had this talk. It's a very, very difficult problem if we haven't had this talk, right? So, but we've had the talk. So, yeah. Right? It's good. I won't even need to grade this one. I'll just be like, all right, same answer again. Everyone's got it. Yay. So the larger question here is, would I expect you to do Calculus 3 style parametrized flux integration on the test in here? The answer to that question is obviously no. I am not a monster. All right? And, you know, so anyway, yeah. All right, any questions? If you do both ways, do you get extra points? That seems fair. Yeah, I should give a bonus. The hooligans are over there now. What's that? If you put units, it'll make me happy, but it won't give you anything. All right, where are we? So I hope that's helpful to you guys. Let me try another example. This one I might get stuck on. We'll see what happens. All right, so suppose you've got, I don't think I've done this one yet. We've got a half circle of charge, all right? And it's uniform distributedly charged, uniform charge distribution. Let's say you've got, you know, Q over the half circle, okay? Radius R, I suppose. And we'd like to know what's the electric field at the point P. Find the electric field at the point P. All right? Now, as I've stated the problem, I'm just kind of relying on the picture, but let's assume that the point P is the origin, right? And so let's just kind of go from there. If I make point P the origin, that would make this point over here, for instance, like what? Like R0, and this guy over here would be, you know, minus R0 for what it's worth. And so if we think about a little infinitesimal charge right here, right? dq. Then where does the electric field from that charge point? Like this, right? But it should be fairly obvious that the left half and the right half of the half circle, what are they going to do? They're going to give you the same sense downward electric field, right? But the horizontal piece of the electric field, they're going to be canceling out, right? Like there's a dual piece of charge over here that gives me electric field that's equally downward but opposite, you know, in the other direction. So I can expect that the net from the symmetry, it's clear that the net electric field here is downward, right? So we can see from geometry and symmetry that the electric field has the form what, like 0, comma EY, right? Wow. So I'm really interested in what's this piece right here, right? So here's my little DEY. I just need to figure out what that is, right? And add those up. So how do you think we should do that here? Like, what's the right way to set up an integration on a circle? What do you think? Yeah.
Would you switch to like polar coordinates?
Right, yeah, switch to polar coordinates is one way to think of it, but certainly we should use an angle, right? So in physics, we make up the angle where we want it to be, and it just so happens that you're right, we'll use basically polar coordinates. We're going to use this angle theta, right? And so like dq, so here are, you know, we have 0 less than or equal to theta less than or equal to pi, right? That's going to sweep us from there all the way over to the other side, yeah? Now, what's the deal? Where is theta in that triangle?
Say the question again.
Where's theta in the the reddish triangle down here. I'll make it bigger. Where's theta down here? My question is like, where would you see theta in this big triangle I'm drawing? It was supposed to be a triangle. I tried.
Is the complementary angle to those two purple lines?
It's, you say it's complementary. Yeah, right. So exactly, this line here that's a line, right? And so the sum of these angles has to be 180. This is 90, right? So what you said was it has to be complementary to theta, right? So that makes this 90 minus theta, right? What's that make this down here? That makes that theta, right? Now dE is the magnitude, it's the length of the triangle here, right? So what's the formula for dEy then? We've got what? We've got like, what? Sine theta times dE, right? But I mean, to be fussy, I guess I should say minus sine theta times dE. I'm thinking of dE as being a magnitude, so I'm putting it is downward pointing, so I'm going to put the minus there. Now, the formula for dE is what? It is, you got your k, you got your dq, and divided by, well, r squared, where r is the distance. And what is that distance? Oh, it's kind of boring here, isn't it? What? Yeah? Yeah, big R, right? So that's the cool thing about this example is the distance isn't variable, right? And how about dq? How does it relate to d theta? Let's think about this. We have dq d theta equals to what? The net change in q over the net change in theta, right? We're assuming that that's uniform. So let's compare the total to the infinitesimal. Like the total is what? We're given q over the whole half circle, right? So I can put q here. And what's the change in angle? Pi. Pi, right. So my formula then is that dq is equal to q over pi d theta. So then I just put that down here. I've got myself k big Q d theta over pi r squared. And all right, so that means my electric field in the y direction is equal to minus the integral of sine theta times k q d theta over pi r squared. And I am integrating from what? From 0 to pi, right? So then how does that integral go? Well, lots of the stuff here is just constant, right? So I got like a minus kq over pi r squared out front, yeah. And then I'm up against the integral from 0 to pi of sine theta d theta. What's the integral from 0 to pi of sine theta d theta? I got to vote for 1. Any other votes? Yeah?
0?
1 vote for 0. Any other votes? Diversity is our strength. Let's get more answers. 1/2. That. Oh, well, we're getting 3 answers. It's even more diverse. Unfortunately, it's 2. Is right. Yeah, it's 2. So see how diversity works? If you just add enough answers, you get the right one eventually. So that's how to explain diversity, in case you're wondering. So there you go, 2kq over pi r squared. Yes. I once taught a large lecture section of Math 115. In that, I got like 20 different answers to one question. 20 distinct answers. That was the greatest diversity I've ever achieved in a math class. It was really good learning that day. Okay, so apparently we've got, and I guess let's put it back in epsilons. 1 over 4 pi epsilon naught is my k. Okay, so we've got, I'm sorry, I regret nothing. Over pi r squared, I'll get out of the way here in a second, 4 pi epsilon naught. Yeah, so I don't know. The formula tends to look prettier with k, but here it is. So we got 0, and then minus 2q divided by 4. You got yourself a pi squared here. R squared epsilon naught. So there you go. That would be the formula for the electric field due to this half circle. Now, there's an interesting problem in the book I noticed, where instead of just having a half circle, they've got something that's kind of similar, but it's like this. So they've got like a circle where they've got, I think, maybe positive charge here, and I'm trying to remember how it goes. Trying to remember how it goes. Maybe they got negative charge here on a quarter circle, and then I think they've got positive charge like on this quarter circle. It's like positive here, negative here, like that. I forget the rest of the problem, but you could just think about this. How would that go? What would the electric field at the origin be for this situation? Suppose this is Q over 2 and Q over 2. Something, there's, to be clear, I'm saying there's no charge over here. There's just charge in the part I've shaded. So there's 2 quarter circles, each with a half a charge. So the electric field should point where? Yeah, it should point towards the, it should point towards that one, shouldn't it? So that would be a little bit trickier than my example 3. We'd have to figure out well, if you left the circle like that, it'd be tricky. A way to make the problem easier is just to rotate the circle so that the, you know, like the quarter circles are like directly over the, you know, cutting through the y-axis. Then you could just kind of set things more up like the last one. Man, they're really rowdy over there today. I don't think I'm ever going to reach that level of shenanigans in here. But not with that attitude. Nice. That's the kind of initiative I'm looking for. We don't have fraternities though, so we'll never really get.
We do.
We do?
Yes.
When did that happen?
There's one frat on campus.
Just one?
Yes.
Wait, isn't it not like a Liberty group?
See, I don't know. I went to NC State, you know, undergraduate, and the stuff you would see during Pledge Week, you saw some things. Like well, you saw some things. My favorite though was I saw this guy running across the brickyard with his tighty whities on, and that was it. And he was running full force, like just booking it. And he caught his toe on something, and he just fell down, just like that. And like a seal, whoop, he popped back up and kept running. It was amazing. It was glorious.
One would even say graceful.
You could say graceful, yeah. You could say that. So you're deprived of that here because we don't have Pledge Week, for the most part, I think. So that one I'd have to really think about. But you could set up these kind of problems very similar to example 3, right? But you'd have to actually like think through. Yeah, when you're faced with a problem like this, you should think about like what kind of answer do I expect? Reduce the amount of calculation as much as you can by using symmetry, right? Like this one, I can see that. I don't know if that really helps. Like maybe I just need to calculate the x and the y separately and just face the music. But I could try to select the component of the electric field that's pointing in that direction for each bit of charge around here, right? The other important trick here for this one is there really any difference between this negative charge up here that's pulling the electric field that way and this positive charge here, which is putting it out? See, the symmetry of the situation says that you could calculate the electric field here by simply doubling the electric field that comes from the lower one. So you just have to figure that out. And to figure that out, we just have to do an integration. But anyway, maybe I'll work that out in the problem session this week if there's interest. So you know, you guys can. So I think in Canvas I've recommended like 10 problems from chapter 21 and 10 problems from chapter 22, and I've worked probably 50% of those in the problem sessions already. I'll try to hit the rest of them in the problem session this Friday, and I think I'm going to be able to record it and post it, I believe. So if you guys have questions about anything else, you know, feel free to shoot me an email. I'll try to cover it in there. Any questions about anything? I think that, yeah.
It's due Monday.
I think that's right. And then Wednesday we have a test, right?
And is there like, is the test Wednesday?
What's that?
When is the test?
Wednesday in class, yeah. We used to have it set up so we could give tests in lab period. We have like 8 labs and like 5 non-lab lab periods, and we just give the tests in there. That was great, but then something happened that we can't do that anymore. So I have to give shorter tests now. It's fine, yeah. But what do I allow you guys for the test? Thinking ahead? 3 by 5 card, right? What do you think the test looks like? It's probably what, like 4 or 5 pages? Probably 4 pages, 5 pages, something like that.
I've been working through your old test.
My old test?
Yeah.
My old test is slightly misleading because it has voltage, it has potential on the first test, which we will not. So our first test in here just has electric fields, so it has like this kind of stuff. By the way, why didn't I use Gauss's law here?
It's not closed.
It's not closed. Like what Gaussian surface would I use that would have a nice symmetry situation? A sphere? But a sphere, it's like, it's not going to be symmetric with respect to the sphere. Like here's another example. So this, you know, sorry to the person who came to my office hours, I'm recycling comment from you, but you know, you got a plane of charge, right? Why don't we put a Gaussian sphere up here and figure out what the electric field is? You know? What's the electric field up here? You know, if you got a sigma, you know, plane charge down here, why don't we use a Gaussian sphere? Right? What's the charge enclosed in this sphere up here? 0, right? And that's equal to the electric flux through the sphere. But is that equal to 4 pi r squared E? Why not? Why do we use spheres sometimes and not always? The geometry of the problem, right? Like this charge distribution down here is not spherically symmetric with respect to this sphere. In fact, whatever electric field comes in that side goes out on that side, right? So this is false, and it is true that the flux of the electric field is 0. I cannot write electric field times area because the electric field varies. See, it's larger here. Well, I guess it's not actually, but you know, it seems like it might be larger there. But the electric field is different. Like the flux that cuts through the sphere is different at different points, because not because of the electric field being interesting, it's actually perpendicular to the plane, right? But because the normal to the Gaussian surface points different directions, different places. So like the flux calculation is quite complicated for this vertical electric field. And yet it's obvious that the field lines that come through the bottom of the Gaussian sphere go out the top, which is why we have a net flux of 0, right? And this is true for any closed surface. The net flux through a closed surface that doesn't contain charge is 0. Whatever electric fields come in one side have to go out the other, basically. Now, if it's a charged, if it's like a charged, not a charged, but if it's a conducting, you know, object, then there's some other funny stuff that goes on in terms of like induced charge on the surface. We've talked a little bit about that already, but the net result is that the electric field goes in one side and goes out the other. But anyway, I think that's all I got for today, guys. So, oh yeah.
Wait, like, until the class, what should we study? Or, like, read?
What should you study? Well, I would say whatever you don't understand is what you should study.
Okay.
That's generally a pretty good plan strategy. I personally, as a student, never did this. When I was studying, I just spent all the time like reviewing the stuff I already knew because it made me feel good. It's like, I know this, I'm ready. And then about like 2 a.m. before the test, I'd be like, oh man, I never studied that section. I guess I should look at that. And then Yeah. I mean, sometimes it turned out okay, but don't be like me. Study ahead of time.